Hi, this is Owen Reno, and this is my project 9 for week 9 over equilibrium. To start, let's look at a brief overview. This is my composite body shown on the right. It's a square pyramid tip with a rectangular shaft and a trapezoidal prism base. We're going to go over a stress field that I have defined, the body force density involving the stress field, and then we're going to look at the total body force on one of my body parts. So this is the stress field I've defined. This is the same slide as the previous week, so I haven't changed what the stress field looks like. As you can see, we have stresses increasing as x1 and x2 increase. Looking at those diagonal components, x1 times x2, that's going to increase these values as looking at this graph here as we get further out from the origin. So that's why these values down here are much larger than what we're kind of seeing near where the tip is at. And so we can also see that the stresses in the x3 direction are going to be halved. Those are a little bit harder to see just based on the stress field I have defined, but those are a portion of this stress field as well. So moving on for the body force density, we can calculate this by taking the negative divergence of the stress field that we have defined. So I've carried over the stress field here and shown that to take that negative divergence, you would just take the gradient of the tensor field. And so we end up getting negative x2 plus 1, negative 1 plus x1, and then negative 0.5. That's what is shown here. And I decided to also show the parameterization for each body, inserting what I have parameterized just for the body itself and inserting that into the body force density. And this is what is being input in the code. And we'll see that later when I show the code. So next we needed to calculate the total body force on the rectangular shaft, and this can be done by taking the triple integral of the body force density of the certain body part times dV. And so I chose to focus this time on the rectangular shaft. And so I carried over the dimensions or the parameters that we're using for our rectangle. So it's 20 by 20 rectangle. So we're starting at negative 10 to 10. And then since the rectangle is in the middle of the composite body, it's going from 0 to negative 50. And so taking the triple integral, it's negative 50 to 0, negative 10 to 10, negative 10 to 10. And it's going to be times the body force density for the rectangle, which is shown here. And this is a pretty easy integral calculation. End up getting negative 20,000, negative 20,000, and negative 10,000, which we're going to confirm with the MATLAB code that this means that this body will be in equilibrium based on my stress field. So let's get out of the presentation here, hop over to the code. We're going to run it. I'm going to scroll up here first. So I'm going to scroll down through this so you can take the time to look at my code if you'd like. The only added portion this time was this body.b4 function. And so I added those for each body part. And so you can take the time to look at that if you would like. And then here's my stress field defined at the bottom. And so we can also take a look at this command window here, and it shows all the total forces on the surfaces and the body parts, as well as the volumes and areas, which add up to what I have got in many of my previous projects. So we know that's still good. But looking at body part 2, when I calculated that total force, like I said, it's in equilibrium because we're getting negative 20,000, negative 20,000, negative 10,000. And so you can also accumulate all the different body parts and get a net force on a composite body. And you can do that the same way by taking the triple integral of each of these other parts and adding all of them together. So I think that's all that I've got for this video. I guess I'll also show that this graph pops out as well, but I've already kind of covered what's going on there. So I hope that you learned something this week from me. Thanks for watching.